As I said in the previous video, a capacitor is a circuit component that is made of two conducting plates that are charged oppositely from one another and are held near each other but not in contact, and its purpose is to store charge. Let's take a look at what the equation for capacitance would be if you have nothing between the plates, and then take a look at what happens if you do put something between the plates. This question asks, what is the capacitance of two conducting plates, each of area 1.00 meters squared, that are separated by 1.00 millimeters of vacuum? The capacitance of a pair of plates is a measure of the amount of charge that the plates can hold per unit 1 volt that is applied to try to charge the plates. And the way that we can calculate the capacitance from the geometry of the plates is with this equation. Capacitance equals kappa times epsilon naught times the surface area of the plates divided by the distance between them. The kappa value is 1.00 if you have either empty space or air between the plates. And again, we'll talk about what happens if you put something else in there soon. But right now, we're just going to put in 1 as our value for kappa. And the value for epsilon naught is a constant, so I look that up and put it in, 8.85 times 10 to the minus 12th farads per meter. Now the surface area is just 1.00 meters squared, and the distance I do want to have in terms of meters, not millimeters, so I convert that over to 1.00 times 10 to the minus 3rd meters. That gives me that the value of this capacitor would be 8.85 times 10 to the minus 9th farads, or 8.85 nanofarads. It's very common with capacitors that you would have the prefixes like micro or nano or pico. A farad is a large value, so you should be dealing with times 10 to the minus exponents most of the time for any capacitor problems. If this capacitor is connected to a voltage source that has 3000 volts, it will store charge. And the amount of charge is related through this equation right here. Q is the amount of charge put on the plates, is equal to the capacitance times the voltage you have applied to it. So now that we have calculated that the capacitance is 8.85 times 10 to the minus 9th farads, we just multiply that by the 3000 volts, and I find out that this capacitor could store 26.6 microcoulombs of charge. That's how these two equations are used. Let's take a look at that kappa. If an insulating material is placed between the plates, then it will increase the capacitance of your capacitor. Of course, if a conducting material is placed between the plates, it destroys the capacitor because it just allows the positive and negative plates to discharge to each other, and now you just have a chunk of conducting material that is not a capacitor. So anything that you put between the plates to increase the capacitance would be an insulator. Another word for insulator is dielectric. So the kappa value in the equation is called the dielectric constant. Let's try to clarify why putting an insulator or dielectric between the plates would improve its performance. When the plates become charged, the insulating material between the plates is subjected to an electric field, and every one of the molecules in that insulator or dielectric is induced to polarize by the presence of that electric field. Notice in this animation, the polarization brings the positive charges closer to the negative plate in the molecule, and the negative charges are brought closer to the positive plate in the molecule. Because this material is an insulator, these charges can't freely move toward the plates, but they can cause their molecule to spin a little bit or to have charge separation inside the molecule. The fact that more positives line up closer to this plate means that this plate would actually be more attractive to negative charges coming from the battery. More negative charges will come in because this insulator polarizes. And over here, more positive charges could be present because of the presence of these negative charges in the polarized material here. The dielectric constant, kappa, for any given material is a capacitance multiplier. It's literally the coefficient that the capacitance gets multiplied by when you put that material between two plates. I do not think that you would be well served by memorizing these values, so it would be a good idea to know where to look them up. In OpenStack's college physics textbook, table 19.1 has them, and if you needed one of these values on a test, I would provide it. Because the dielectric is improving the performance of the capacitor specifically by the material being polarized by the presence of the electric field, it actually turns out that a molecule that is already polar makes for a better dielectric. That's why on this chart you can see at the bottom the dielectric constant of water, which is a polar molecule, is very large. So you may be looking at this explanation of polarized molecules and wondering, what is it exactly that I need to be able to do? Let's see an example question and an answer to clarify that. In this example, it says an ambitious student attempts to make their own capacitor by sandwiching a piece of standard-sized printer paper between two sheets of aluminum foil. Each one is a surface area given by 8 inches by 10 inches. Assume the sheets are pressed together airtight. So the two aluminum foil sheets will be separated only by the thickness of the paper, 0.076 millimeters. And unfortunately, standard size printer paper is given in inches, so we would want to convert that over to meters before doing our calculations. The questions we are asked are, what is the capacitance of this setup? If this capacitor is wired to a 9-volt battery, what voltage would the aluminum sheets be compared to each other? What is the amount of charge that these sheets would hold? And what amount of energy could this capacitor store? Before we try to calculate the answers, I would like to take a look at this page right here, which is from the chapter review at the end of chapter 19 in the OpenStack's college physics textbook. This looks like 4 different equations, but actually it's 3. This is the equation that I used earlier. Q equals CV is how I had written it in the previous problem. But I had defined earlier that the capacitance of two plates is a measure of the amount of charge they can hold per unit voltage. And that is what this is right here. I'd like to emphasize that capital V is voltage, and the reason I'm emphasizing that is because down here we have capital A for surface area and D for distance. So sometimes students think in terms of surface area and distance and try to put a volume in here. That's not what that is. This is our voltage. Now I said it looks like 4 equations, but it's really only 3, and that's because they provide this equation right here, which is really like a JV version of this equation. The capacitance can be calculated from the geometry of your capacitor if you know the surface area of the plates, the distance that they're separated. Epsilon naught is a constant, so again you can look that up when needed. And then kappa is your dielectric constant. This equation up here is presented as though kappa doesn't need to be there, because kappa is 1.0 if you are doing a problem where the plates are separated by vacuum or air. I would prefer to think of this as the equation and then substitute in 1 as needed for your kappa value. Don't think of these as 2 separate equations at all. And then in the example problem, it was asking us about the energy. So we do want to notice that the energy stored in a capacitor is equal to Q times voltage divided by 2, or you could substitute in different versions of this. These 3 different equations down here are really the energy equals QV over 2, and then they have given different versions of it where they've substituted in capacitance as part of that equation based on this. They rearranged it for Q or V and plugged them in here to get these different versions. So back to the question, what is the capacitance of this setup? Well, the size of the aluminum sheets, I converted over to metric, is 0.2032 meters by 0.254 meters. And then I can put it into this equation where the capacitance of the 2 aluminum sheets divided by the printer paper comes out to be 3.7 as the dielectric constant of paper, which I don't know. I had to go look that up, and I would expect you to be in the same situation. Times epsilon naught, 8.85 times 10 to the minus 12 farads per meter, times the surface area of the aluminum sheets. And notice that I didn't actually calculate what it is because I don't really care. I'm just going to put this times this as the surface area, divided by the thickness of the paper, because that's how far apart the aluminum sheets are if they are only separated by the printer paper. And from that, I can calculate that the capacitance of this setup that the student has devised is 22 nanofarads. So you absolutely can make your own capacitor out of a couple sheets of aluminum foil and some printer paper in case you need to, I don't know, MacGyver your way out of some situation in real life. Part B of the question was, if you take this capacitor and attach it to a 9-volt battery, meaning one of the two aluminum sheets is attached to the positive side of the 9-volt battery and the other aluminum sheet is charged from the negative side of the 9-volt battery, what voltage will the aluminum sheets be compared to each other? And this is kind of a trick question because the whole point of attaching it to a 9-volt battery is to charge the two sheets to be 9 volts separation from each other. So the sheets will be charged to whatever the voltage was of the battery. What amount of charge would these sheets then hold? Well, Q equals C times V, and we just calculated C. So 22.2 nanofarads times 9 volts. And I calculate that therefore the student's devised capacitor could hold 200 nanocoulombs of charge. The amount of energy it could hold, I would then go back and find one version of that energy equation. I've put it in the equation here as capital U to emphasize that this is a electric potential energy, just like we had actually been talking about in the previous section. I don't really care if you call it E or U, as long as you make sure that you're using a valid version of the equation, some version of the equation that is correct. So 1/2 times the capacitance times the voltage squared is the version I chose to use. And the reason for that, I think, is because I found the capacitance first and then the charge. And I don't really want to use Q in this equation if I can help it, just because sometimes I make math errors and I don't want that to carry over into the next step. But I do get the 1/2 times the capacitance times the voltage squared comes out to 0.9 microjoules of energy. That's how much energy I could store in my 200 nanocoulombs of charge with my two pieces of aluminum foil that are separated by a single sheet of printer paper. So that's a quick example of how we could use a dielectric or insulator between two charged plates to improve a capacitor and how we would do some calculations with that setup.